Right, today we're going to cover Physics Paper 4. This is from May-June 2018 and it's variant 2, so the code is 0625/42. Now this is for the Cambridge IGCSE from Cambridge International Examinations. Alright, let's begin.
Let's get started!
Question number 1. Figure 1.1 shows the axis of a distance-time graph for an object moving in a straight line. There we go, okay. So it's an object moving in a straight line. We've got the axes, that's why there's no line on it. That makes sense. So it's basically saying we've given you the graph and we haven't done anything with it. There is no line yet. 1. On figure 1.1, draw a line between time t equals 0 and t equals 10 for the graph. For an object moving with a constant speed of 5 meters per second. Alright, let's just have a look at how this actually works. Moving with a speed of 5 meters per second. So we've got a speed of 5. And time. And how far has it moved? Okay, time 0 is moved no meters. Time in seconds, distance in meters. If its speed is still 5 meters per second, and time is 1 second, it's going to have moved 5 meters. So literally just distance is speed times time. After 5 meters a second, it's going to, after 2 seconds, have moved 5 meters twice, that's 10 meters. And of course, after 3, it's going to have moved 15 meters. You can see we're just multiplying these out. Absolutely fine. Okay, so what we need to do is put that into our graph and go all the way to time t equals 10. In fact, let's just put that down here. If time is 10, it's moving at 5 meters per second, then I know it's going to have travelled a distance of 50 meters, so it's going to be up here. And I can mark these individually if I want. I should get a nice straight line. I don't have to. I can just go from the start, 0, 0, all the way up to that point I've just marked. But let's just have a look at it. At 2 seconds, it should have travelled 10 meters. That's there. 4 seconds, it would have gone 20. 6 seconds, it would have gone 30. 8 seconds, it would have gone 14. See this beautiful straight line forming. So let's just draw in a nice straight line here. Join all the points together. Come up to the end point. They are perfect. You can see it goes through all the points. Part 2. State the property of the graph that represents speed. Well, the speed is actually given by the gradient of a distance-time graph. There we are. 2. Between time t equals 10 seconds and t equals 20 seconds, the object accelerates. The speed at time 20 seconds is 9 meters per second. Calculate the average acceleration between those times. Alright, well, let's put down our first equation. Acceleration equals change in velocity divided by change in time. In fact, let's just write in the actual words. There we are. Now this is something to do a lot in these questions. They give you a distance time graph or a speed time graph, then ask you to calculate acceleration, but acceleration uses velocity, not speed. Yeah, and it's an important thing. So they might give you a distance time graph and ask you to calculate the velocity, but velocity uses displacement, not distance. So does it matter? No. It matters when they ask you for definitions, but when they've given you this much information, you have to use the information they've given you. You have to use the fact it's the speed. Forget it's the fact it's should actually be velocity. You write in the acceleration, change in velocity over change in time. And just use the speed as if it's velocity. From the graph, you would just use the distance as if it's displacement. They do this a lot. It's quite woolly. It's a bit frustrating because you spend a whole, good few lessons going through the difference between speed and displacement and velocity and distance. Those things, people say it's so important, and you get to the exam at the end and the exam board just kind of ignored the differences. So we're going to do the same. We ignore the differences, and that's what you should be doing in your exam unless they're asking for specific differences between them. So change in velocity, well, it ends up at 9 meters per second, and it starts off at 5 meters per second, and it does this in a time between 20 seconds and 10 seconds. So that's going to give you a value of 4 meters per second divided by 10 seconds, which in fact will give you 0.4 meters per second squared. Now, I know it's one significant figure here, it's one significant figure here, but for these exams you don't want to use less than 2 significant figures. and you don't really want to use more than 3. So, despite the fact it's 1 and 1, I'm going to use 2 for the number of significant figures here, 0.40 meters per second squared. Alright. B, figure 1.2 shows the axis of a speed-time graph for a different object. The object has an initial speed of 50 meters per second and decelerates uniformly at 0.35 meters per second squared for 100 seconds. Ooh, that's interesting. So you got a situation where accelerations change in speed, or change in velocity divided by change in time, which means that the change in velocity will just be given by the acceleration times the change in time. So I'm just going to calculate the change in speed because the acceleration is 0.35 meters per second squared, and the time that it's decelerating for is 100 seconds. And that's going to give me a value of 35 meters per second. Now, it's decelerating, so that means it's getting slower. It's going to be 35 meters per second slower at the end than it is at the start. Okay, now on figure 1.2, draw the graph to represent the motion of the object. Well, we know it starts off with a speed of 50 meters per second up here. Now it gets 35 meters per second slower by the end after 100 seconds. So 50 minus 35 will give me 15 meters per second. And that is how slow it will be travelling at the end. It is a constant acceleration, so the gradient will be constant. It's a straight line graph. Part 2. Calculate the distance travelled by the object from time t equals 0 to time 100 seconds. Alright, so for this we're just going to be calculating the area under the graph. Now, probably the easiest way to do it, certainly the way I find easiest anyway, is just to break it down into 2 shapes. One, this big old rectangle down the bottom. It's not a very straight line, but assume it is. Okay, and the area of this rectangle will just be 15 meters seconds multiplied by 100 seconds, and the area of the triangle at the top would be 1/2 times base times height, 1/2 times 100 seconds times the height, which is 50 minus 15. It's 35 meters per second. So there we go. That's the calculation we'll perform. Now, 3 marks here. Whenever you see one of these questions, whenever you see it, the very first thing you want to do is write down the distance travelled as the area under the graph. There we go. There's almost always a mark available for that. So now let's put down the calculations, make sure they're nice and clear for everyone to see. There we go. So we've got our calculation down. 35 times 100 times 1/2 plus 15 times 100. And that will give us 1750 plus 1500. Which is 3250. Alright, now let's just look at this calculation again. What we can see is that's one significant figure, so the answer shouldn't really be to more than 2 significant figures. So let's put 3300 meters. And there we go. That's our final answer. Excellent. Question 2. Figure 2.1 shows a hollow metal cylinder containing air floating in the sea. There we are. A. The density of the metal used to make the cylinder is greater than the density of seawater. Explain why the cylinder floats. Okay, so the cylinder floats because the total density of the container is less than the density of the seawater. There we go. So the cylinder floats because the total density of the container is less than the density of seawater. B. The cylinder has a length of 1.8 meters. It floats with 1.2 meters submerged in the sea. The bottom of the cylinder has an area of cross-section of 0.8 meters squared. The density of seawater is 1020 kilograms per meter cubed. Calculate the force exerted on the bottom of the cylinder due to the depth of the seawater. Alright, so the force exerted on the cylinder pushing it up will be equal to the weight of the water that the cylinder has displaced. So because of that, if we know the volume of the cylinder that's under the water, we can multiply that by the density of the water. And that will tell us the weight of the water displaced, which is equal to the force pushing the cylinder up. Alright, so if the force is equal to the weight of the displaced water, then the weight of the water would just be the density of the water times the volume displaced times gravity. Because volume times density would get me the mass, mass times gravity gives me the weight. So let's put in our figures. So there we go, that's 1020 kilograms per meter cubed multiplied by 0.8 meters squared, that's the bottom area, multiplied by 1.2 meters, which is the amount that's submerged in the sea, so not the total length, just the amount submerged, multiplied by the value of gravity, which is 10 meters per second squared. There we go, and that gives me a value of 9792 newtons. Now let's just look at our significant figures. That's 3. Here is actually 2 because there's a 0 in the question. I didn't write that in. 2 significant figures there. And this one at the end, the 10 meters per second squared, that's just one significant figure. So that means really we shouldn't be going beyond 2 significant figures. And of course for this type of exam paper, should be doing 2 or 3 significant figures as a general rule anyway. So we certainly wouldn't want to leave it as 1. So I would think 9800 newtons. So a wonderful answer there. There we go. Let's move on to the next part, part C. Deduce the weight of the cylinder and explain your answer. Okay, well the weight of the cylinder will be equal to 9800 newtons. That's the force that's pushing it down into the water, and it's being met by this force pushing it back up. The explanation, how do I know that's a force? Because the resultant force equals 0. So there's a force pushing it down, which is its weight, and the force pushing it up, which we worked out, is 9800 newtons, and I know that the resultant force is 0, so the weight must be 9800 newtons. Question 3. Figure 3.1 shows an aircraft on the deck of an aircraft carrier. The aircraft accelerates from rest along the track. At takeoff, the aircraft has a speed of 75 meters per second, and the mass of the aircraft is 9,500 kilograms. Calculate the kinetic energy of the aircraft at takeoff. Alright, this is worth 3 marks. Straight away, what we want to do is write out our equation for kinetic energy. Kinetic energy is 1/2 mass times velocity squared, which in this case is 1/2 times the mass of 9,500 kilograms multiplied by velocity squared, which is 75 meters seconds negative 1 squared. And that will give us a value. Here we go, let's just look at significant figures. 2 there, 2 there. Ooh, we could treat that as a 1. So we'd expect the significant figures to be 2 significant figures. That's 2.7 times 10 to the 7 joules. There we go. Don't forget your units. Very important as well. Right. B. On an aircraft carrier, a catapult provides an accelerating force on the aircraft. It's true, it's actually driven by steam, if memory serves. The catapult provides a constant force for a distance of 150 meters along the deck. Well, certainly it used to be driven by steam. Don't know if it still is. Calculate the resultant force on the aircraft as it accelerates. Assume that all of the kinetic energy at takeoff is from the work done on the aircraft by the catapult. Right, so we want to calculate the resultant force on our aircraft here. So resultant force. Now, as you know, force is mass times acceleration. Now, we know that it travels a distance of 150 meters. We know from part A that the final speed v is 75 meters per second, and we want to find the acceleration. So we need an equation which links acceleration, final velocity, displacement, and the other thing we actually know already, we know the initial speed is 0, it's from rest. So we need an equation which links all of those things. And luckily enough we have it. V squared equals u squared plus 2as. And we can rearrange that to get the acceleration. Acceleration is v squared minus u squared divided by 2s. And now we can put the information in. So that's 75 meters per second squared minus 0 squared divided by 2 times 150 meters. Excellent. That should get us the acceleration, and the value that that will give us is 18.75 meters per second squared. Alright, way too many significant figures here, but this isn't the final answer, so we're not going to change it yet. Now we put it straight into our F equals ma equation. So we want to find force. Force is then going to be equal to mass, 9,500 kilograms, multiplied by the acceleration, 18.75 meters seconds negative 2, which gives us 178,125 newtons. There we are. Alright, so let's just look at this. What do we have? See where all these numbers come from, how many significant figures we should use. 2 significant figures, 2 significant figures, 1 significant figure. So let's do the answer to 2 significant figures. That's 1.8 times 10 to the 5 newton. Yeah, 1.8 times 10 to the 5 newtons. Excellent. There we go. Let's move on to question 4. Question 4, figure 4.1 represents an atom. Isn't it lovely? Representing atoms by circles approximately the same size as in figure 4.1. So it wants us to try, if we can, to make sure that the things we're going to draw are about that big. Sketch on figure 4.2 the arrangement of atoms in a crystalline solid. Okay, so atoms in crystalline solid. And on figure 4.3, atoms in a gas. So solid and gas. Well, let's look at it. And let's begin with, say, figure 4.2. What we're going to do, try and get them, roughly the same size as that one. So there we go, there's our atoms in a crystalline solid. All the atoms are jammed in closely together, they're tightly packed, and they're all touching. Now, gas, much easier to do. There's an atom, and there's an atom, and there's an atom. Problem solved. Excellent. So that's our atoms in a gas and atoms in a crystalline solid. 1 mark for each of those. B1. Describe the motion of atoms in a solid. Well, look at the solid. You've got to draw another arrow to it. Not much in the way of motion. All they can do is vibrate about fixed positions. 2. A sculptor makes a statue from a block of crystalline rock using a cutting tool. Explain why you must apply large force to the tool to remove a small piece of rock. Well, what he has to do when he breaks those bits of rock apart is he's got to overcome the forces between the molecules in the rock. And that's actually what's happening. So let's put that down. So there we go. Forces applied must be large enough to overcome forces between molecules. C. A helium-filled balloon in the room of a house suddenly bursts. State and explain in terms of atoms what happens to the helium from the balloon after the balloon has burst. Okay, well, the helium molecules are going to collide with air molecules and are going to diffuse about the room in all directions. There we go. Helium atoms collide with air molecules and diffuse about the room in all directions. 5. A student wants to investigate good and bad absorbers of thermal radiation. She has the apparatus shown in figure 5.1, a supply of cold water and a meter rule. Explain how the student could use the apparatus she has available to carry out her investigation. Describe the results she would expect to obtain. Draw a diagram of the setup. Okay. Well, let's look at it. We have an electric heater. We've got a couple of cans. I think what we want to do is fill these cans with water to the same level. Probably put the thermometers inside. And then put one on either side of the electric heater at the same distance, and then that would tell us which one is good at absorbing thermal radiation, which one is not as good as at absorbing thermal radiation. So let's do that, and let's put that picture underneath down here. Alright, so there we go, there's a diagram of the setup. Now let's explain what we're going to do. We're going to want to turn on the heater. The heater should be an equal distance from both of the cans. The can should be filled with the same amount of water in each can, and the thermometer should measure the temperature change. You should be able to then compare the two temperature rises to find out which can is the better absorber. So there we go. Place cans in equal distance, 10 centimeters from the heater. Fill cans with the same amount of water. Put thermometer in the same positions in the cans, in the water. Turn on the heater for 10 minutes and measure the temperature change. Expect a higher temperature change in the black can, as black is a better absorber. Let's just add that there and make sure it's nice and clear. As black is a better absorber. There we are. Question number 6. Circle 2 of the following that apply to an ultrasound wave travelling in air. So ultrasound's anything above 20 kilohertz, 20,000 hertz. Okay, so here we go. Frequency is above 20,000 hertz. Circle 2 that apply to an ultrasound wave travelling in air. Well, it's also longitudinal. There we go. The speed, you'll be looking normal speed of sound in there, which is about 330 meters a second. None of those are close. So two that apply are those two. Frequency 35,000 hertz, and it's a longitudinal wave. B. Calculate the wavelength in a vacuum of X-rays of frequency 1.3 times 10 to the 17 hertz. Well, straight away we know that C equals F lambda. C in this case is 3 times 10 to the 8 meters per second. So we rearrange that. Lambda equals C over F, which is 3 times 10 to the 8 meters per second, divided by our frequency, which we've just been given, 1.3 times 10 to the 17 hertz. And that will give us a value of 2.3 times 10 to the minus 9 meters. There we go, we've got two significant figures, one significant figure there, so we should have two significant figures over here in our answer. 2.3 times 10 to the minus 9 meters. Remember your units, there's nothing written down there. Okay. C. A dentist takes an X-ray photograph of a patient's teeth. Explain why it is safe for the patient to be close to the source of X-rays, but the dentist must stand away from the source. Well, that's actually going to be because the dentist is exposed to X-rays often. So the total dose on the dentist would be much higher over time. D. State with the reason why microwave ovens are designed only to work with the door closed. Well, that's actually because microwaves are harmful to humans, especially in the concentration that they're in microwaves. Much more powerful than you get in a normal, say, a phone. So microwaves are much more powerful. So microwaves generally can be harmful to humans, especially at that power. And they would easily pass through the open door of a microwave oven. So you have to close the door. And if you look at the doors, you'll see they've got those tiny little holes in them, little round holes. And that's to prevent the microwaves coming out, because they're far too small for the microwaves to effectively travel through. But visible light can, so you can look inside and see your food cooking. So there we go. Microwaves are harmful to humans. They would easily pass through the open door of a microwave oven. Question number 7. Figure 7.1 shows a ray of light in water that is incident on a submerged, transparent plastic block. So we've got a situation here where what we already have is light in water travelling into plastic, which is also in the water, one would assume. State what happens to the speed of light as it enters the plastic block. Explain your answer. Alright, so one mark for saying what happens and another mark for saying why. Okay, well straight away I can actually tell you what happens. The speed that light is travelling at decreases as it travels from water to plastic. How do I know that? Because the light bends more towards the normal line. It would normally be travelling in that direction. It's bending towards this normal line here. And that means that the speed is decreasing. So there we go. The speed light is travelling at decreases as light bends towards the normal. B. Figure 7.2 shows the two principal focuses, f1 and f2, of a thin converging lens. Figure 7.2 also shows an object O of height 1.2 centimeters placed close to the lens. Two rays from the tip of the object O are incident on the lens, and they've been drawn in. We can see them there. On figure 7.2, continue the paths of these two rays for a further distance of at least 5 centimeters. Okay, so let's come back up to that diagram there, and we'll continue those two lines for at least 5 centimeters. So I'll just take them to the edge of the graph there. So let's draw in the first one. There we go. And let's draw in the second one. There we are. That's those two lines drawn. Let's see what the next question is. 2. Use your answer to be 1, the one we just did. Find and mark on figure 7.2 the image I of the object O and label this image. Right. Well, as these lines aren't coming together as we move off to the right, we have to go to the left. We continue the lines to the left until they meet. So let's just do that now. So there we are. I've continued the lines up until they meet. Now let's just draw that in and label that with an I for the image. And there we go. We've drawn that in, labelled it with an I for the image. Let's just make that line a bit clearer so you can see it. If you're watching that, there we go. Oh. Well, do your arrow a bit more neatly than I did mine, especially in the exam. Part 3, determine the height of image I. Okay, well it's on a grid, so we can just go straight up there and count the squares. Okay, so this comes all the way up to that point there. There we are. That's 1 centimetre, 2 centimetres, 2.8 centimetres. There we are, that's the height of the image. How do I know the scale? Because it's written down here. There we are. Part 4, state and explain whether I is a real image or a virtual image. Well, in this case, it's a virtual image. Why? Because it cannot be projected. It's on the wrong side of the screen. It's on the same side of the screen as the object. So it's a virtual image because it cannot be projected. And there we are. Let's move on to question 8. 8. Figure 8.1 shows a circuit that contains a battery of electromotive force, 6.0 volts, an ammeter, a 20 ohm resistor, and component X, mystery component X. A1, state the name of component X. Well, this, here we are, is a variable resistor. That's a symbol for a variable resistor. Let's put that in now. Two, the potential difference across the 20 ohm resistor is measured with a voltmeter. On figure 8.1, draw the symbol for the voltmeter connected to the circuit. Okay, so the voltmeter is outside of the circuit and across the resistor. There we go. Make sure that these lines all join up. You don't have any little gaps. You put a little gap and you will lose marks. There's a risk that you have to be aware of. Make sure that the lines form continuous lines. If you have a small gap, for example, here we go, like so, it's clear that you know what you're doing. Doesn't matter, you do not have a complete circuit there, you may not get the marks. So make sure that everything is attached correctly. B. The potential difference across the 20 ohm resistor is varied from 0 to 6 volts. For each value of potential difference, a corresponding current is measured. On figure 8.2, draw a line to indicate how the current measured by the ammeter depends on the potential difference across the 20 ohm resistor. Okay, well, what we're going to do is we're going to assume that this 20 ohm resistor is working well. We know that V equals IR, and we know that I equals V over R. Now I can put in different values for the voltage and come up with values for the current. Now I know it's going to be a straight line graph, so what I can do is just find the value at 6 volts and draw a straight line from 0, 0 all the way up to whatever value that is. So let's put this in. I at 6 volts would be equal to 6 volts divided by our 20 ohm resistor, and that would give us a value of 0.30. amps, obviously. Make sure to put that in. So what I can do is put a value, I'll put a cross up there for that point, and then draw a straight line between 0, 0 and that point. Now, of course, you could always you could always calculate the values of the current at the different voltages and do it that way. You'll find that they all appear on that line. If you want to do that, that's absolutely fine. So if you want to, you'd find you get a point here, a point here, a point here, and you just calculate them out and you would find them that way. But because I know it's going to be a straight line, I can put in the value of the 6 volts, avoid that altogether, and just go straight to the end. Problem solved. C. A second resistor is connected into the circuit in parallel with the 20 ohm resistor. State how the combined resistance of the two resistors in parallel compares with the resistance of each of the resistors on its own. Well, if you're doing it in parallel, then the total resistance will actually be smaller than the smallest resistor in that sequence. So the combined resistance will be smaller than the smallest resistor. Part 2. The potential difference across the two parallel resistors is changed, and the current in the battery for each value of the potential difference is measured. A second line could be drawn on figure 8.2 to indicate how the current measured by the ammeter depends on the potential difference across the two resistors in parallel. So we know that the resistance is going to be smaller. State how the second line differs from the original line. You're not expected to draw the second line. Okay, well, let's just do a brief little example here. I know that I equals V over R. As resistance gets smaller, the current gets bigger. So I'm going to see a steeper gradient to the graph. And of course, because we're still dealing with perfect resistances, then it's still going to be a straight line graph. Question number 9. Figure 9.1 shows a coil ABCD with 2 turns. The coil is in a magnetic field. When there is a current in the coil experiences a turning effect. Explain why there is a turning effect. Well, it's pretty straightforward actually. What's going to happen is one side of our coil, here we are, would experience a force up, and the other side would experience a force down. So the force is in opposite direction. It creates a turning effect. Depending on the direction of the current, of course, the forces could be in opposite directions, but it would just mean it would turn the other way. So as one side of the coil is pushed up, the other side of the coil is pushed down, i.e. AB is pushed up and CD is pushed down. 2. The value of the current is 3 amps. Place 1 tick in each column of the table to indicate how the turning effect changes with the change described. Okay, so the number of turns on the coil is increased to 6. So we started off with 2 turns. We've gone to 6 turns. That's 3 times the number of turns. That means there's 3 times the amount of force being generated. So the turning effect increases by 3. The current is increased to 9 amps. Well, it was originally 3 amps. It's now gone to 9 amps. That's 3 times the amount of current. So 3 times the amount of turning effect again. And finally, the strength of the magnetic field is decreased by a factor of 2. Okay, well, if the magnetic field is decreased by 2, then the force on each side will be decreased by 2 as well, and the turning effect decreases by a factor of 2 as well. B. Figure 9.2 shows a magnet held just below a vertical coil connected to a galvanometer. The magnet is released. State any effect on the galvanometer. Well, what you're going to see in this situation is you're going to see the galvanometer switch to one side and then switch back. Maybe to the right, maybe to the left. It depends on how it's been set up. So it will deflect and then return to 0. 2. State any effect on the magnetic field produced by the coil. Well, it produces a magnetic field to oppose the motion of the magnet. So it produces a magnetic field to oppose the motion of the magnet. 10. An uncharged conducting metal plate rests on insulating supports. Figure 10.1 shows a plate and a positive charged insulating plastic sheet placed on top of the metal plate. 1. Describe any flow of charge that takes place when a plastic sheet is placed onto the metal plate. Well, what we can see, of course, is the plastic sheet has positive charges on it. It's a positively charged plastic sheet. So what we're going to see is the negative charges move towards the plastic sheet. The negative charges in the metal plate move towards the plastic sheet. So the negative charges in the metal move towards the plastic sheet. 2. On figure 10.1, draw how the charges are now arranged within the metal plate. Okay, what you would see is a bunch of negative charges up close to the positive charges, and underneath them you'd see the positive charges because the negative charges didn't come from nowhere. There we are. There's a neutral plate going in, it's still a neutral plate, but the charges have been separated. 3. State and explain if this arrangement of charge helps to keep the plastic sheet in place. And yes, it will help to keep the plastic sheet in place because opposite charges attract. And there we go. B. Figure 10.2 shows two uncharged conducting spheres suspended on insulating threads. 1. Each of the spheres is now given a positive charge. On figure 10.2, draw a possible position of each sphere and thread. So there we go. What you see, of course, is that the two positively charged spheres would repel. 2. Explain the positions that you have drawn. Well, like charges repel. And there we go. Let's move on to question number 11. 11. A radioactive nucleus of uranium-235 decays to a nucleus of thorium and emits an alpha particle. Complete the equation. Okay, so we got thorium, we got uranium-235. Let's look at this. What we know is that numbers at the top remain the same. What do I mean by that? 4 plus whatever thorium is will equal 235. So that tells me that thorium must be 231. So I haven't lost anything on top, and I'm not going to lose anything on the bottom either, on the charge. I've got the same amount of positive charge at the end as I did at the start. So that tells me that 92 equals whatever thorium is plus 2. It must be 90. Let's write that in as well. And there we go. B. A nucleus of uranium-235 undergoes nuclear fission in a reactor. Explain what is meant by nuclear fission. Okay, well, nuclear fission happens when we get heavy nucleus splitting apart to form smaller nuclei. So heavy nucleus splitting to form smaller nuclei. 2. Suggest why a nuclear reactor is surrounded by thick concrete walls. Okay, well, the thick concrete is going to help to absorb dangerous radiation from a nuclear reactor that is released when the nuclei split. So the thick concrete will help to absorb the dangerous radiation from the nuclear reactor that is released when the nuclei split. 3. State one environmental advantage and one environmental disadvantage of using a fission reactor to generate electrical energy in a power station. Well, the advantage is no CO2 is produced, and the disadvantage is there's a long-term danger from nuclear waste. C. The thorium produced by the decay in A is also radioactive and has a half-life of 26 hours. At a certain time, a pure sample of this isotope initially contains 4.8 times 10 to the 9 atoms. Calculate the number of atoms of this sample that decay in the following 52 hours. Ooh, that's interesting. Look at that. It's asking the amount of atoms that decay, not the amount of atoms that are left. So let's look at that. Alright, so I start with 4.8 times 10 to the 9 atoms. I undergo one half-life, and that 4.8 will change into 2.4 times 10 to the 9 atoms. I undergo another half-life, and that 2.4 will become 1.2 times 10 to the 9 atoms. Now let's look at this. The half-life is 26 hours, so this will take 26 hours. This will take another 26 hours for the second part, which then takes me to 52 hours. So it's 2 half-lives. This is the amount I have left. But again, it's not asking how much is left. It's asking how much has decayed. Alright, so I want to know the amount that's decayed. The amount decayed is equal to the amount you started with minus the amount left. So let's put in some numbers. So that will give us 4.8 times 10 to the 9 minus 1.2 times 10 to the 9. Which gives us an answer of 3.6 times 10 to the 9. So the number we're left with is 3.6 times 10 to the 9 nuclei. And that is the number that have decayed. Alright, so that's the end of the paper. Hopefully you enjoyed that and you found that useful and helpful. If you did, please feel free to like and subscribe. And if you have any comments, please leave them in the comment section below. And you know what, guys? Have a great day.